Okay, so welcome everybody to the third talk of GADEP seminar. So today we have Haohua Deng from Duke University, who is going to speak about space of nilpotent orbits and extension of period mappings. So please, Haohua.
Yeah, thank you very much, Roberto, for inviting me, and it's my great pleasure to talk. And so let me introduce this talk is based on the work by these two papers, one by me. So if by me alone, the first, this is a series. I plan to make this a series. The first paper is already submitted, and this archive number. And the second, well, is it just maybe in progress, should be coming soon because So the second one is joined with Colleen Robles, and we are just finalizing some mode writing the paper, and it should be coming soon. And hey, this is the outline of the talk. So I plan to talk about some basics in Hodge theory and also reviewing some very classical results. So after that, we'll just talk about what's the main target of this work and also what's the main results we have got so far. Okay. So let's begin with some really elementary things. So the Hodge theory. So when we say about the integral polarized Hodge structure, we mean a collection of data, which means we have an integral polarized lattice HZ and polarization from Q. And besides this, we are going to have a filtration, called Hodge filtration on the complexified vector space, as well as its weight and Hodge numbers, such that there are some specified conditions specified numerical conditions should be satisfied. So the Hodge numbers, the weight, and also for the polarization form, we should have the isotropic condition and positive definite condition. Okay, so this is a general definition for integral polarized Hodge structure. And for such a data, we consider what's the classifying space of all such integral polarized Hodge structure. Well, so we denote this D as the classifying space, or say the period domain of the set of the integral polarized Hodge structures with the prescribed data. And as a comparison, we also have its so-called compact dual, which is compact, as of course. And this just is the classifying space of all of the semi-Hodge flags. By semi, we mean we just have every condition of a Hodge flag, but just we drop the positivity condition. Right, positive definite condition. So indeed, in general, this D check is projective, and D is a real open real semi-algebra subset of D check. So in this case, both of them and their tangent space, are agreed, and also they can be realized as real or complex homogeneous manifolds with the action of their real or complex automorphism group, GR or GC. And I would say, the tangent space can be identified as the quotient of this Lie algebra, where this Lie algebra quotient, this F0GC on the Lie algebra, is given by the induced Hodge flag on the endomorphism group. Okay. So these are some basics in Hodge theory. So we have the definition of the Hodge structures and the period domain. So now let's consider what is variation of Hodge structures, or VHS. So in general, to be convenient, we just focus on some very nice space. So now we say S to be a quasi-projective variety and fix the projective completion S bar such that this S bar minus S is a simple number crossing divisor. So this is in general, the basic setting when you want to play with the asymptotic of Hodge theory. So we say a variation of Hodge structure is integral local system VZ over S. And we also put a filtration of the Hodge bundles on the corresponding vector bundles of this local system. And we also need morphism of the local system from V to V cross V to a twist of Z, such that, well, if we consider on each stock, we must have on each stock VS, QS, and this filtration should give you an integral polarized Hodge structure, of course, of weight L. And also, it requires that the corresponding connection of this vector bundle, the vector bundle corresponding local system, should satisfy the Griffiths transversality. So this is the basic setting of an abstract VHS. So in general, in algebraic geometry, such an VHS could be like so. It's very frequent, can be obtained from, for example, a family of smooth projective varieties. And these families, we just push for the integral local systems on the total space. And in this case, we can just on a fiber wisely, we just get the Hodge structure of the corresponding fiber, which is just by our assumption is a smooth projective variety. Okay. So indeed, this is a very the common tool in when we take a look on the deformation of algebraic varieties by looking on their associated VHS and period map. Okay, so any integral VHS, we have associated period mapping, so we just map the base S to, so it intuitively speaking, we want to map to its associated Hodge structure, but polarized Hodge structure on the fiber. But to identify each fiber, the cohomology of the fiber to a fixed vector space, we have to use analytic continuation. So using this analytic continuation will lead to an ambiguity by the monotonic group. So indeed, we are mapped this S for such a VHS. We have a map from S to not D, but D, but quotient by the monotonic group of this VHS. And in general, we know, so this gamma by D, this quotient space, it has a structure of complex analytic variety, and phi is a holomorphic mapping. Indeed, this holomorphic can be very well interpreted. Indeed, it is the algebraic part and transcendental part is very highly restricted. Okay. But by the way, so our goal is to, so for such a given period mapping, so either abstract or coming from a geometric family, we want to see if we can find a suitable extension from S, this phi, from S to S bar. So because we want to find, extend this phi to the compactified base S bar, and the image is in a suitable extension of this gamma by D. So in this talk, in our work, we are going to use the Kato-Nakayama-Usui space, which I will introduce later. And also, if we have such a Hodge theoretic period mapping extension, we also want to find some algebraic geometry examples on which, we can, to study the degeneration of algebraic varieties, we can study that by studying the Hodge theoretic degeneration of this period mapping. Okay. So yeah, so this is the first part. So please feel free to let me know if you have any comments or questions. Okay, cool. So let's go to some known cases, which are the classical cases. So let's see what if we focus on the case when this D, the period domain, is a homogeneous symmetric domain. Okay, so these are called as the classical cases, and it is most known in general, by classical we mean that these two cases when the first is the weight 1 and Hodge number is given by this is G and G, or weight 2 and H20 should be 1. So this is the Calabi-Yau weight 2 Calabi-Yau type, right? And in these two cases, it is well known that D is homogeneous symmetric, and indeed in geometry, there's well-known application that in the first case, because we have the period mapping from the moduli space of polarized abelian varieties, which gives you a period map from this moduli to the quotient of the gamma by D, where D is the period domain for weight 1 Hodge structures. And also for the weight 2 and H20 equals to 1 case, we had used that to study the moduli polarized case-free surfaces. And we know that in these two classical cases, it's the period mapping is faithful in terms that we have the global Toroidal theorem, which allows us to recover the geometric object by using just Hodge theoretic information. Okay, so these are the classical cases. And for the classical cases, this compactification of this locally symmetric variety gamma by D, and of course when gamma is arithmetic. So in this case, the commodification of such a locally symmetrical variety is very well studied, right? Because there are many famous works on this. And for example, if we take a look on the rank G single alpha half space, single, maybe I should say this is a single space, and the single space is SG is the quotient by HG. By an arithmetic subgroup, this HG should be the single alpha half space. And this case, we know like this is the this is like we have the period mapping from the curves of genus G to this to this single space. And it's well known, like, so we have the maybe just say two most well known commodifications. The first is the Satake Borel, which is like, so we are adding cusps around infinity. And set theoretically, this SG compactified by SBB is given by the disjoint union of SG itself with all the lower dimensional single spaces. Okay, so this is a canonical construction. And there's another like very well known, which is the Mumford's Toroidal commodification. So this commodification is finite, but it is not canonical because it depends on a choice of gamma elements of polyhedral decomposition. And there are like more than one such decomposition known. And what we have is that if we choose this sigma good enough such that the space constructed by Mumford Toroidal commodification would be as good as a smooth projective variety. Okay, so as a comparison, Satake Borel construction is a projective, gives you a projective variety, but it is very singular because you have cusp. And you can understand like the Mumford Toroidal is indeed like the resolution of SBB. So in general, like so the Mumford Toroidal commodification carries like some more information than SBB. So I believe like so maybe many of you already know like so the construction and the background of these two constructions. I mean in the classical theory of locally symmetrical varieties, but I would like to give you like so a Hodge theoretic description of these two constructions. So the first is that the single alpha half space is Hg or say Dg, which is the period like isomorphic to the period domain of with one Hodge structures. So this like describes or contains all the pure Hodge structures of type GG. And if we draw this Hodge-Deligne diagram, right? So this can be described in this dot diagram. And this is DG, right? So and if of course you are taking the quotient. So you are taking like so up to a gamma equivalent class of such pure Hodge structures. But what about on the boundary? So the Hodge theoretic boundary degeneration can be described by these limiting Hodge structures, or say just sometimes if we are not considering a specified period map, you just say the mixed Hodge structures. It is described by, well, another Hodge-Deligne diagram, which like so we have a non-trivial weight filtration and a Hodge filtration, and we combine them both. We have a Deligne splitting for the mixed Hodge structures, and such a Deligne diagram can be described by. So as you see in this example, all of the limiting Hodge structure type can be described by this Hodge-Deligne diagram where you move the 1, 0 and 0, 1 part to 0, 0 and 1, 1 part. Okay, so these are described by such Hodge-Deligne diagrams. Okay, so I guess like so this 1, 0 should be G minus A here. Okay, and as you see, the Satake Borel type boundary components on the boundary for these limiting Hodge structures, the SBB boundary components encodes information about the graded pieces of these mixed Hodge structures, because right, so when we consider the graded quotient of this weight filtration, then F induces pure polarized Hodge structures on each graded quotients. And in this case, you see in the graded quotient 0 and graded quotient 2, we only have a single point, so they are trivial. The only non-trivial piece is the graded 1 case, right? So in this case, we have pure Hodge structures of type G minus A, so it has a smaller rank. But yeah, so this is exactly encoded by the SBB type boundary components. And as you see, it just like so. It's agreed with the previous construction that the SBB type boundary components should be the lower dimensional single spaces. But however, for the Mumford toroidal compactification, we like the Mumford toroidal boundary components does not only contain information about the gradient quotients, the Hodge structure and gradient quotients, but also the extension data of corresponding mixed Hodge structures. So the fiber, it is indeed like a fiber. It has a fiber structure along the SBB type boundary components. And geometrically, so let me introduce what type of geometry information can be encoded in these two type boundary components. So let's take a example. So this is a degeneration of genus 2 curve. When we degenerate, so for example, we choose a 1 parameter degeneration or 2 parameter degeneration. It degenerates in the central fiber, it degenerates to a node. And you have this node, you have this nodal curve, singular code on the central fiber. You find a normalization, which gives you a genus 1 curve with 2 marked points, which are the pre-image of the node under the normalization. So in this geometric model, when we consider the Hodge theoretic degeneration, so of course for the smooth curve, you have the pure Hodge structure of type 2,2, and around the degeneration fiber, you have the logarithmic Hodge structure, which is type 1,1,1,1, which described as mixed Hodge numbers. And in the right-hand side, this genus 1 curve, of course, if you consider its Hodge structures on this first cohomology, you have this type 1,1, right? Type 1,1 pure Hodge structure. So in these cases, the SBB boundary components, isomorphic to H1, right? So in this case, from the SBB boundary components, we can read off what is the pure Hodge structure on the first cohomology on this normalized curve, right? So this is isomorphic to the first cohomology. It parameterizes the Hodge structure on this H1 C tilde Z. But however, if you move to the Mumford toroidal compactification on the toroidal boundary components, we should not only read the first cohomology group on this normalized curve, but also the extension data that tells you what's the image of the Abel-Jacobi map, the image of this P minus Q, this device on this C tilde under the Abel-Jacobi map. Okay, so you can read some more information from the toroidal boundary components than only the SBB. And indeed, so if you check, so there's some analysis on what, in this case, what are exactly the shape of this toroidal and SBB boundary components. So the SBB boundary components, of course, as we talked before, it is a one-dimensional single space. The toroidal boundary components in this case should be isomorphic to an elliptic modular surface. So if you have interest in knowing more about this Hodge theoretic boundary components, you can see, I think, the Kerr-Pilstein's work back in 2016. So where they classify some very nice examples on what are these Hodge theoretic boundary components look like. Okay, so these are the story for the classical cases. So before I move to the non-classical cases, so I'd be happy to answer any questions if you
have. Can I ask a question?
Yeah, please.
So in this case, you just degenerate to one node. But yeah, if I understand correctly, if you degenerate to 2 or more nodes, there's a abelian variety part of the fiber. There's also a toric part of the fiber. Do you know how to interpret the toric part in terms of an extension?
So in that case, if you have 2 nodes, I think so this Hodge the Hodge the Lin diagram it gives you Hodge state degeneration, which means in coordinates so the logarithmic Hodge structure would be Hodge state. You have 2 on the 1,1 part, 2 on the 0,0 part, and nothing on the graded 1 part. Okay, so in that case, I think the toric part is described by the extension data of the Hodge state logarithmic Hodge structure. Okay, so let me see if I can draw on the let me draw. So in that case, if you have 2 nodes, I think the LNHS you will get is this. And in this case, the extension data, right? So you have cusp, right? In this case, so the SBB is just a point, but the cusp, so if you consider toroidal, it gives you a extension data of this LNHS, which should be C2, C star 2. Is that what you're asking?
Yeah.
Yeah. So anyway,
I guess.
Yeah.
That's good.
Is that good? Okay, sure. Thanks.
What was the reference? Can you tell me the reference again that you said?
Okay, so it is by Kerr-Prosty. 2016, like so, it's like so the boundary components of Mumford domains, if I remember correctly. It's the Duke Mass Journal paper. So this like so consider like so even more general setting, not a period domain, but also the Mumford domain. But there are some nice examples. Yeah, you can read some many good examples and calculate what are the exact Hodge theoretic boundary components. Okay. Any other questions? All right. So then let's move to non-classical cases. So in the non-classical cases, well, of course, like so one want to think of like if you can apply this, because these classical stories are very good on describing either like so constructing a Hodge theoretic compactification of the moduli space, but also describing the degeneration behavior of geometric objects. So of course, one think of like so whether we can find like so a generalization of the story is to the non-classical cases. So this is like so this is a long-standing problem. So and like so let's say like so one think of this like right this geometry versus Hodge theoretic picture. And like so some objects like this are like so surface of general types, when like so you have the like so the H20 is not necessarily 1, or you have like so higher weights, for example, Calabi-Yau threefolds. However, like so in these non-classical cases, when like so means like the D is no longer Hermitian symmetric, it is almost impossible. Like so it like looks impossible, right? And I'm not saying definitely impossible, but looks at this time there's like so no idea of how to find a good compactification of this gamma by D, or even for our purpose, we are not finding a full compactification of gamma D, but if you only want to just find what's a compactification of the image of this field map, okay, so this S2 gamma D is, I mean, the image of this phi. These questions in the non-classical cases are very open at this point. So for example, like so, I didn't wrote here, so but I want to introduce like so for the second question to find a completion of the image of peer map. So there are some no one works in recent years. So for example, in Baker, Brumbaber, and Zimmerman's paper, they proved that by using the O-minimal method to prove like so the image of such a peer map should always be quasi-projective. So they proved that by proving like so the augmented Hodge line bundle can be extended to the boundary, and like so this is an ample line bundle. But however, like so that does not include like so much information on what's the behavior on the boundary. And also like so the Green Griffiths, Robles, and Raza, so they proved like they have another construction on proving the image of the period map can be they find a completion of the image of such a period map, which they call the generalized SBB type compactification, because on the boundary they also encode the graded quotient of limiting Hodge structures. So the space they constructed in general is only an analytic constructible space which are stratified by analytic subvarieties. But in general, like so, to prove that it has some nice global properties, it is open. I think they only prove like so for two-dimensional period map, or say as it has dimension 2. In that case, the image the completion space they constructed is projective. But for all other cases, they are like so still open. So what are exactly the space they have been constructing? But now let's talk about Kato-Nakayama-Usui, or originally Kato-Nakayama-Usui, but later generalized by Kato-Nakayama-Usui to mixed Hodge structure case. So the Kato-Usui's theory is developed in the very beginning of the 21st century. So they are trying to find a Hodge theoretic completion of period mappings. And later, like so, as I said, like so, it is generated by Kato-Usui plus Nakayama. They have another series besides Kato-Usui's book. They wrote another series of papers generalizing their theory to the mixed Hodge structure case. And like so, what are the main tool they have been used? So they are indeed they find very nice reinterpretation by using the logarithmic Hodge theory, which is some kind of the modern techniques to reinterpret some classical results like the Schmid's nilpotent orbit theorem or CKS, their as multivariable SL2 orbit theory. And what are the spaces? The spaces they constructed contains the nilpotent orbits. So to introduce their method, we have to know what are nilpotent orbits, right? So these comes from some classic works by Schmid and Kato-Nakayama-Usui. So let's give it a quick review. So a nilpotent orbit, a sigma and f. Sigma we choose to be a polyhedral cone in the rational Lie algebra of the automorphism group G, and we require that it should consist of nilpotent elements. It should be commuting nilpotent elements. So I missed a very important condition. So commuting, which means the subspace generated by the sigma should be abelian under the Lie bracket. Okay, so we have a abelian commuting nilpotent elements consisting of this cone consisting of commuting nilpotent elements. And this F is a semi-Hodge flag in D check such that we should have the Griffiths transversality by this cone acting on this Hodge filtration. And also we want on the sound direction, if you multiply this exponential of this on the imaginary part, IYN, and multiply on this F, it should eventually dive into the period domain. So if you want a picture on this, so if this is the period domain and this is the compact dual, it is larger. So originally you have an F only in D check, but by acting by any elements in this cone, it should eventually dive into the period domain, right? So it cannot go to some other direction. So this is not allowed. So you should eventually dive into inside the period domain as long as this y tends to infinity. Okay, so this is a very rough picture on what is a nilpotent orbit. And Schmid's nilpotent orbit theorem, Schmid's nilpotent orbit theorem, not nilpotent theorem, nilpotent orbit theorem. So Schmid's nilpotent orbit theorem says that roughly, if you have a local period map, this delta star to the n to gamma by d, and if you take any p on the boundary on this disk, we have a canonically associated nilpotent orbit, but this orbit this is up to local monogamy. So up to local monogamy group, we can associate any boundary points on this delta star to the n nilpotent orbits. Okay, and in general, if you have general period map where the space is not necessarily local, normal crossing, not locally, the managed locus of the coordinate axis, you still have a nilpotent orbit defined for points over S bar minus S, but however, such a nilpotent orbit is only well defined up to global monogamy group, just like with the period map, right? So the image of the original period map, the point in this D is well defined up to the global monogamy group, and the similar thing happens for the nilpotent orbits. So this is the Schmid's nilpotent orbit theorem, which tells you that indeed this set theoretically well-defined map, right? So you can just map any point in S to its associated nilpotent orbits by Schmid's nilpotent orbit theorem. So this motivates the idea that Kato and Usui use the space of nilpotent orbits to be a proper candidates for the extension of this period map. So the image of the period map, right? So what kind of object you want to map to? So the nilpotent orbits. So this is the motivation. And I think in their work, they are interpret this story in terms of their own logarithmic Hodge theory. And this is called the logarithmic variation of polarized Hodge structure. And indeed, these two concepts are, at least like for some good base S, they just coincide. So let me introduce like what is the type of the objects we are going to obtain from Kato-Nakayama-Usui theory. So based on the period domain D, we construct a D sigma, where this capital sigma is a collection of nilpotent cones, and this D sigma is consists of all such pairs sigma z, such that sigma is a cone inside this chosen collection, and this z should be a sigma nilpotent orbits. Okay, so there's a very obvious inclusion from the original period domain, because if sigma, you choose sigma to be just a zero cone, the trivial cone, you have this, right? So the set of the set of points in D check to give you your nilpotent orbits for the trivial cone is just the period domain itself. So you have an obvious inclusion of D to any such D sigma. And this sigma, this capital sigma, is called it's a collection of nilpotent cones, but it should have some much finer structure according to Kato-Nakayama-Usui theory. So the sigma should be a gamma strongly admissive polyhedral fan. So indeed it should be a fan, okay? And it should be a fan, and it should have a strongly admissible structure on the gamma. So I won't give the technical definition of this sigma, but I just want to let you know that the collection of the sigma should be a fan, and also it should have some very nice and highly restrictive structure on this fan. And our expectation is that if we have such a collection, such a fan exists, then suppose this period map, one can extend this to this phi to phi bar on all of the S bar, and the image should be extended from gamma by D to gamma by such a D sigma if the sigma contains all of the local monogenic cones of this period map. So this is the expectation, right? So we are extending this phi to phi bar, and the image lies in the quotient of this quotient by gamma of this space D sigma. And what happens if we have such an extended map? So if such a sigma exists, then this quotient space would be carry a structure called the logarithmic manifold. So this is a very special structure. So one can understand and the definition of this is very technical because it uses some very complicated definition in logarithmic geometry. So, but one can just understand as locally, it looks like analytic constructible space, which means you just piece together analytic spaces of different dimension, and this piece is not arbitrary, so it should be given by locally. It should be given by the logarithmic structure, indeed, the mentioned locus of some logarithmic differential form. To give you a naive example, so let's consider this. So this is one of the naive example that understand what do logarithmic manifolds look like. So indeed, it is excuse me. Locally, it is modeled by the C2, but you just drop this coordinate axis. But after you drop this coordinate axis, you add 1 point, this 0, 0 point back. So you can see this is kind of analytic space, but there has some slits, right? So there has some slits. And the strata by analytic subspaces has some abnormal different dimensions, sorry. And also, this is the local model of a logarithmic manifold. And once we have this space, then this S bar to this logarithmic manifold, so this map, this phi bar, this extended map, should be a morphism in the category of logarithmic manifolds, which means locally it should preserve the logarithmic structure. So these are some nice properties. And what is even nicer is that Usui also proved in 2005 that even before their book was published, that if we have such an extension, okay, suppose we have such an extension to gamma by d sigma, the image of this extended map in this gamma by d sigma should carry a structure of complex analytic space, which means like so you can indeed patch up together all the complex analytic structure on each strata and patch them to a global one. So this is a very nice property about the period image in this space. I mean, period image in this extended period map. And I would just like to say like a word about their original goal is that, I mean, originally like so Kato and Usui like so they use a much more general settings than us, like than me like so what in my work. They are trying to construct a fine moduli space of all logarithmic variation polarized Hodge structure, and they prove that if you have such, you can find such a fan sigma, and you construct such a space gamma by d sigma, which is a logarithmic manifold, then any LBPHS, or say like so, just you can understand like so, BHS on a basis which you have a nice compactification, you always is classified by the morphism from such a basis to this logarithmic manifold. So maybe I should say is this would be if you have a like so if you have a like so VHS, for example, or say like so logarithmic variation Hodge structure on some basis, whatever the basis is, as long as this VHS has the given set of data, then you have a unique morphism of logarithmic manifold from that S bar to this constructed Kato-Usui space. So this is a very ambitious goal because they want to compactify a very large group of VHS together within this one space. Okay, so after introducing our expectation, right? Like so before, like I just said, like, so suppose such a construction works. So now we have to talk about, okay, so does it really work? So the main problem is that how to construct such a fan, okay? The sigma, because as I said before, the sigma should be, sigma should not only be a fan, consists of the nilpotent cones, but also it should carry a very strong structure, which is called a gamma strongly admissible polyhedral fan. Okay, so does it exist? The answer is yes, in some cases, for example, in the classical cases, because indeed, their definition of the gamma strongly admissible case condition exactly coincide with the Mumford's Toroidal compactification in ANRT. So in Ash, Mumford, Rappaport, Tai, in their book, they construct also the gamma admissible polyhedral decomposition for the classical cases. And in classical cases, their definition of this fan indeed agree. And if you use this fan to construct a Kato-Usui space, the consequence is coincides with the toroidal construction of Mumford. Okay, so in the classical cases, they produce the same result with ANRT. So in this sense, sometimes like so maybe some people would call it like a generalized toroidal compactification, but like so I just say the Kato-Usui is extension. Okay, and besides the classical cases, for any cases, indeed, for one-dimensional period maps, for the like so one-parameter period maps, it is also trivial that we have such a fan exist because we can just. So let me just say like a word about why this is trivial. Because just take the adjoint gamma class of all local monogenetic nilpotent cones, but in the one-dimensional case, all of them are rays, right? So if you take so at the end of the day, you just get a bunch of rays, and it is clearly a fan. And if you take the adjoint gamma class of all of these local monogenetic nilpotent cones, the resulting fan is indeed, by definition, has a gamma strongly admissible structure. Okay, so for the one-dimensional period map, such a construction is immediate. So I think there are some applications by many people when you apply this Kato-Usui theory on the family of mirror-quintic Labial threefolds, which has the Hodge number 1111 in that case, you only have one-dimensional period map, and you can use the Kato-Usui space to study what are these one-parameter degeneration. Okay, so this is something very well known. But however, what if the most general case, right? So if you have a non-classical period map, you cannot apply Mumford's toroidal compactification, and you have multi-parameter VHS, which means multi-parameter means you have some 2 or more higher dimensional cones, and if you just like so paste them together by using the adjoint action of gamma, you might have some bad intersections, which prevents that collection to be a fan. So indeed, in general, this is a very open and hard problem. And the first, I mean, in my thesis, this is like one of the main results in my thesis is that I find the first example, like so for the 1-2-2-1 family. So this is the first example where we have a non-classical multi-parameter period map such that we can find such a Kato-Usui's construction. But however, recently, I and also my my collaborator Colleen Robles just our joint work found some more such examples where we can indeed apply such a construction. So the first result is in my first paper, and the first paper I just mentioned at the beginning of my talk. So suppose we have a period map of Calabi-Yau-3 type and type 1H1. This H is in general it can be 2, 3, or anything else, but in general just greater or equal than 2. And suppose along the boundary, so boundary means the bound degeneration of this period map, we only acquire type 1 and type 4 limited mixed structure. I've explained what do this mean later. So if we only acquire some specified type of degenerations, or say the limited mixed structure, then we can find a finite proper modification is S bar, let's say S bar tilde. So this finite proper modification mean maybe it's a finite sequence of resolution and a finite base change like this. And this actually does not destroy the algebraicity or some other nice properties of the base. So after doing this finite proper modification, then we can find such extension. And this space I wrote here is not d sigma, but d sigma phi. So I will also say what does this mean. But indeed, you can just understand this as a slightly modified version of Kato-Usui extension. So first, let me explain what did I mean by type 1, type 4. So indeed, all of the possible type of limited mixed structure of a given, for example, for the Calabi-Yau-3 fold, the weight-3 Calabi-Yau case, are classified by work by Kerr, Perlstein, and Robles. So they have in their paper they classify, for example, for the Calabi-Yau weight-3 Calabi-Yau cases, they classified all possible Hodge-Sterling diagrams for the degenerations, and all types can be for in one of these 5 types. The 0 type is the pure case, type 1, type 2, type 3, type 4, and these are you can just understand by you can draw the Hodge-Sterling diagram and read the information from them. So as you see, if along the boundary components we only acquire 2 of them, right? Type 1, type 4, there's no type 2 or type 3 degenerations, then we can find such a extension period map. Such a construction by Kato-Nakayama-Usui after using a finite proper modification. So this is the main result in my first paper. And also, I also mentioned I was using a slightly modified version of Kato-Usui space, which is d sigma phi instead of only d sigma. So this is a very modified version, and the space.
Just a question.
Yeah, please.
This maximal unipotent monodromy is included in your.
Oh, of course, because type 4, right? Type 4 you have. Yeah, type 4 because type 4 means you have cube is not 0. Okay, so of course the Hodge-Tate case is included. So yeah, and I said in my first paper, I have to use for some very sneaky technical reasons. I have used a slightly modified version of Kato-Usui space, and this will be a slightly different from the original Kato-Usui space. It won't be a logarithmic manifold in general, but only a locally analytic constructible space. But however, it acquires some good properties, including the image should be carries a complex analytic structure. So that should be like so roughly regarded as good as Kato-Usui's compactification. So this is the main result in my first paper. And in my second paper with Robles, so we should be coming soon. In this paper, we just consider like some more general, but only two-dimensional period map. So suppose we have two-dimensional period map, but like so Hodge numbers could be very general, right? It's not only Calabi or threefold case, but very general period map of very general Hodge numbers. And we say that if the degenerations of this period map are good enough in terms like so we have some technical conditions on the local monodromy cones, then we have the similar results that after finite proper modification, we can find such a Kato-Usui extension. And in this case, we don't have to do any modification, just use the original Kato-Usui's construction. So this good enough degeneration. So I don't think like so. Do I have time? I mean, I don't think I will be able to present those numerical conditions here. But I just want to give you one of the most exciting corollary from this work is that any type 1, 2 to 1 period map would admit such an extension after some finite proper modification. So which means like so. So in my previously, as I mentioned in my graduate thesis, I proved that I just find one example of type 1, 2 to 1, but now we are able to prove that for any such type period map, you can find such a Kato-Usui extension. I believe that there are many examples in mirror symmetry, and in those families coming from mirror symmetry, we always have such a Kato-Usui's construction after finite proper modification. Okay, so this is one of the most exciting corollary from our works. But however, if we have some higher, so it's a higher rank, for example, in general, for the weight 3 Calabi cases, but H is larger than 2, in this case, we cannot say any period maps admit such a construction, but we require some further numerical conditions on some certain type of degenerations. And at the larger H goes, the more restrictive our condition goes. But for the 2 case, when H is 2, then there's no restriction. And like I say, any period map admits such a construction. Okay. So let me say something about what are the techniques I use in these papers. So in the first paper, what I was doing is I tried to re-interpret the classical weight 1 case. So recall that the ANRT, also the Mumford toroidal compactification, they are trying to find a smooth projective compactification. Yeah, maybe I should say this just gamma sigma 2. So this should be right. So this is the ANRT's work. They are trying to compactify the whole locally symmetric variety gamma by D. But however, I was trying to reinterpret the idea, but using a Hodge theoretic language to only find a partial compactification of this locally symmetric variety gamma by D, which compactifies the image of a given period map, right? So this would be much less ambitious than ANRT. The results are weaker. But the good point is that by using these techniques, by using the KNU and Hodge theoretic language, we will be able to generalize. There's a direct generalization from this classic weight 1 case to weight 3 case, right? So the good point is that there's a direct generalization. There's a bridge to be built between the classical weight 1 case and weight 3 case. So this is not visible it seems to me that this cannot be done by using ANRT's theory, but can be done by using the Kato-Usui's language, as shown in my first paper. And I just give you a very rough picture on how this works. So for example, the type 1 limiting Hodge structure is something like the Hodge diagram. But however, as you can observe, the only part impacts the monodromy operator, this n, right? This monodromy logarithm. This monodromy logarithm has nothing to do with the graded 3 part, right? So there's a way that we can try to exclude this irrelevant graded 3 part, such that we can just relate the monodromy cone in this case with a monodromy cone in the classical weight 1 case. So we just find a way to delete this irrelevant weight 3 part and twist it by some z minus z1, and we move to the classical case. And similarly for type 4, yes. So for type 4, if you consider is you restrict to a subspace and take the quotients, you also have a shape of the classical cases. So in these two cases, for the type 1 case, the monogenic cones are faithfully present in this transition, because you are just the part you are excluding has nothing to do with the monogenic operator, right? The monogenic logarithm just annihilates all of them. But in the type 4 limit Hodge structure, after you're taking quotients, you are losing one-dimensional information in the weight 3 case, right? Because in the weight 3 case, there's a one-dimensional map you are quotienting out. So you are losing something, but not too much. So there's a way to fix the loss of this information. So indeed, this is the idea, how we can, using Kato-Nakayama-Usui language, we can build a bridge between the classical weight 1 case and this two certain type of weight 3 Calabi-Yau type degenerations. And in my second paper with Colleen Robles, we are using some different techniques. So in our second, because we are considering the most general period map and degenerations. So our methods, one of the central techniques in our work, is relying on controlling a suitable family of nilpotent orbits near infinity. And this is a kind of partial generalization of some classical results. So first, in Schmid's original paper, one of the results he obtained in his chapter 5, I think, is that suppose we have the local lift of a one-dimensional period map. So a local lift of the period map can be written in this way. So the first part is the algebraic part, and the second part is the transcendental holomorphic part. So suppose this is the local lift of one-dimensional period map, then you can find a single Siegel domain. Okay, so Siegel domain in D, S in D, such that the image of this local period map, when restricted to some strip, like a small strip, is contained in this Siegel domain. So indeed, because for the one-dimensional period mapping, the local lift would be a map from the Siegel upper half space to D, right? So in Schmid's original paper, he proves that if we restrict the local period map, the lift of local period map to a region bounded on the real direction, but just goes to infinity on the imaginary direction, the image of this strip is contained in this single Siegel domain. Okay, so this is one of the classical results. And this result is recently generalized by Becker, Klinkler, Zimmerman in their paper, such that Schmid's result can be generalized to multi-variable case, where if you have a local lift of the multi-variable period map, and you consider restricting each of these variable into this strip in the upper half space, then the image of this multi-variable local lift or period map restrict on this multi-strip will be contained in finitely many Siegel sets. Okay, so not necessarily a single one, but finitely many Siegel sets, Siegel domains. So this is one of the most technical results in their paper. Also, a key ingredient for them to prove the definability of period map. If you know about the O-minimality series, so they prove in their paper, they proved the period maps are all definable in terms of the algebraic, restricted analytic, and exponential. So that's and this theorem will be the key ingredient in their paper. But however, my paper with Robles, use a generalization of these two classical results. I won't say the second one is classical, but the second one is a very recent result. Okay, so we proved that we can use finitely many Siegel domains to control not only a single period map or specific, in particular, a nilpotent orbit, but instead a family of nilpotent orbits varying on even non-horizontal directions. So this is the method to be used, but I'm not able to show like some precise statement because that stimulus took like 20 pages to prove. But anyway, so okay, so finally, because I claim that our works prove like so for any 1221 type period map, like so we have such a construction. So I want to just finally I want to give you a picture on what do like so all possible degenerations of such a period map look like. Okay, so the type 1221 degenerations can, in terms of their elliptic Hodge structures, besides the pure degeneration, so these are all possible degenerations characterized by their Hodge-Deligne diagrams, and these are classified by Colleen and Robles. So as you see, the type 1, type 2, type 3, type 4, I mean, there are only 7 possible degenerations in these cases. And we can describe, if you don't like the Hodge-Deligne diagrams, you can also use the numerical characterization. I mean, just you have like so just put some restrictions on the monitoring logarithm, and in some cases you might also have to use the Hodge filtration. But anyway, so these are all possible degenerations for the 1221 period map, and all of these period maps satisfies our numerical conditions, so we can find such a Kato-Usui construction and prove our theorem. Okay, so that's all I want to say. So thank you for your attention.